Good afternoon all, and welcome to Timber Development UK's webinar series on engineering with timber. This series aims to add to your engineering education so that as we transition to a bio-based economy, you have the tools and knowledge to include timber within the projects you work on, whether new build or retrofit. My name's Tabitha Binding. I work for Timber Development UK as Head of Education and Engagement. Toby, would you forward the slide, please? So Timber Development UK has been formed from the merger of two of the largest and longest established organisations in the supply chain, the Timber Trade Federation and the Timber Research and Development Association, which you will also all know as TRADA. Next slide, please, Toby. So TDUK are seeking to connect the supply chain, lead best practice, and accelerate a low carbon future. Next slide, please. So today, I'm delighted to have Beth and Toby as our speakers and guests. But just as before we get underway, our platform is Zoom meetings so that you can communicate with us and with your peers. Please post any questions in the chat and we will come to them at the end of the presentations. Our speakers today are civil engineer and passive house designer Beth Williams and structural engineer Toby Maclean, and they will delve into how buildings should go together. They will look at what happens at the junctions between floors, roofs and walls and consider how to ensure good practice that will lead to durable and robust buildings, which is surely what we all are aiming for. With a focus on the construction typology for low-rise buildings, discussions will cover the advantages of timber in different forms, detailing against the risks of moisture and fire, acoustics and thermal performance. So with that, I'd like to hand over to Beth and Toby to introduce themselves.
Thanks, Tabitha. I'll start. So just a little bit about us before we dive into it. So my name's Beth Williams, as Tabitha said. So my background is in small practice. I do a lot of new build homes, and as a passive house designer, I do a lot of low energy and other passive house and other low energy standards like the AECB building standard buildings, and with a focus on timber and low carbon design. So Toby, what would you?
Yeah, I'm Toby Maclean, and I'm a structural engineer. As you can see, I work for All Environmental Engineers, which is a practice I started a few years ago, with the aim of really getting to grips with how we decarbonise the built environment with an emphasis on embodied carbon. And been learning quite a lot in the last few years.
Thanks, Toby. So what we're going to focus on today, here's some examples of some projects that are like the ones we're going to look at. This timber detailing is a massive topic that we can't cover all of it today in just an hour, but what we're going to focus on, because it's mostly Toby and my experience in practice, are domestic scale timber buildings. We're going to look at the details working up from the ground floor up to the roof in how you might approach them. We're going to look at sawn softwood timber because that's most common detailing in the UK. And then we're also going to look at engineered timber, I-joist construction. We'll mention CLT and other types of engineered construction as well. So yeah, working from the ground upwards and focusing on domestic scale buildings. There's obviously a lot more to say in terms of detailing for large scale timber buildings, but we'll keep it narrow today. And then, so to focus our attentions, the main themes of our topic are going to be keeping timber dry and not letting it burn. So we'll be talking about those two things throughout the detailing, because those are the main focuses for detailing with timber. So yeah, to start with, I'll pass over to Toby to get started.
Okay, thanks, Beth. And as Beth just mentioned, if you're short on time, you can probably leave now. These are the two things that are really important with timber detailing, and I can't emphasize that enough. Now, what we'll be doing is going through a notional building from ground up, looking at kind of typical details and pointing out what's done and why in each case. Again, concentrating on low-rise, typically single-family occupancy houses, but we will touch on larger buildings towards the end, and happy to see questions on those as well. So without any further ado, here's a fairly typical ground floor foundation detail for a traditionally timber-framed building, a house. There's quite a lot going on here. And in terms of the resistance to moisture, that is keeping it dry, one of the main things we're doing here is keeping the timber above ground. So the 150 dimension to DPC from external ground level is fairly important. We make sure that DPCs, damp-proof courses, below the lowest point of all timber. So that's below the timber walls and external walls, but also for timber walls off ground-bearing slabs inside, etc. There's a suspended floor here, which is by far a timber suspended floor, which is by far the lowest carbon way of doing a ground floor. And that will always have a ventilated void below it. The depth of that void depends on the ground type to some extent. It can be higher with clays because they might heave up. And it should be ventilated and drained. Don't forget the drainage of that area, and making sure you've got active drainage. So if water does get its way in under the floor, it can get out again. In some sites, that can be tricky. This detail has a brick cladding on the outside. And behind brick cladding, you'd always have a 50mm cavity before you get to the insulation or timber frame. And again, that's just to make sure that if moisture does get past the brick, it doesn't make its way to the timber. The brick cladding has open perpends. Those are the vertical joints between bricks in each section. And that's all specified in the building regulations. Again, just to make sure that there's some ventilation to it. We'll see in the next slide, there's greater ventilation required on other types of cladding. And then when you go to the inside face of the cavity, against where we've got the blue insulation shown there, there'll be a breather membrane. Now, breather membrane is a material which lets air through, but will be a first defense for moisture, again, should moisture reach the cavity. Bearing in mind we have got brick ties in there. And on the inside face of the insulation, on the warm side, there'll typically be a vapor control layer, that's called a VCL on these drawings, which prevents warm, humid air from inside the building, making its way into the colder areas of the insulation zone where it could possibly condense. In terms of fire and not letting it burn, with traditional timber frame, you'd almost always be encapsulating enclosing the timber in a fire-resistant material like plasterboard. There are some other notes here. On the external side of the timber studs, which are the vertical yellow shading here, there'll always be a sheathing board, typically OSB. Again, that'd be OSB class 3, which is more suitable for slightly humid environments. And where necessary, for stability, we might need to hold the timber frame down. And there are some straps showing in this detail. Whether you need those or not depends on your calculations and whether you actually get overturning on your stability walls. Thermally, we've got insulation between the joists and studs. In the 80s, that might have been all you needed between the studs. These days, with much more stringent requirements on thermal insulation, you're almost certain to need insulation either inside and outside the studs as well. I've chosen to show the insulation outside the studs as well as between them in this example. Beth will cover some later where you've got much wider studs where they're wide enough to cover all the insulation. And you'll see on the inner leaf of the cavity wall below ground, there's technically a thermal bridge, a cold bridge from ground up into the floor. It would be possible to put a thermal break, some kind of foam glass as a course in the blockwork there, if you were worried about that. And just to keep things really simple, I've summarized some use classes. Use classes are refer to the environment that timber will be in and how susceptible it will be to decay, where generally speaking, the higher the use class, the worse the environment, the more onerous the environment. And that's a quick summary. But do think in each case about whether the use classes will be worse than typical. There's an asterisk there against BS 52685 because although that's useful for looking at use classes, it does include some preservatives which shouldn't be used these days. The next slide is very much the same as the last one, except I've just switched to timber cladding. I'm only going to cover the differences here between the timber cladding and the brick cladding. And you'll see there's a kind of a wider zone behind the cladding where we've got some battens. So in this case, I'm showing some vertical battens and some horizontal battens because we've got vertical cladding. If you have horizontal cladding, you wouldn't need the horizontal battens, obviously. You do need to create a cavity. Typically, that would be the width of the battens, about 38 mil. And you would need to ventilate above, at the top and bottom of each section of cladding. So more ventilation required on timber cladding than on a brick cladding. And that applies to pretty much to any rain screen cladding. So it could be a render board as well, instead of the timber cladding you see here. The fire, stability, thermal insulation, all much the same as before. And use class is just a note there about the cladding and battens. There is some very good guidance from TD UK in their cladding handbook, by the way, on cladding. Now, the next slide I'm going to show you is a world first. You won't find this detail in any guidance. And you'll notice in this slide, the ground level is conveniently much lower than the internal floor level. And in real life, it can be quite hard to achieve that sometimes, not least because of accessibility requirements to buildings. Occasionally you can locally change ground near the entrances, but not always. And I'm not aware of any published guidance for ground level being the same as the internal floor level. So here we are, world first. If you do find any published guidance for this, send it to me, I'll give you a small prize. Be slightly wary in adopting this because A, it can be more challenging, and B, there may be some warranty providers that are a bit uncomfortable with the idea that the floor joists here are below ground level. And on that note, the floor is clearly much more vulnerable to moisture because it is below ground level. And the detail shown here is to dress the DPC from under the sole plate down the inside face of the wall behind that timber wall plate that the joists are fixed to. So there's a break for any moisture which gets through both sleeves of the cavity. In this situation, again, we need to ventilate and drain the void below the floor because we're further below ground. It could be more difficult to drain the floor, possibly impossible to drain the floor, depending on the water table and the site topography. So do treat these as typical details, but not always appropriate to all circumstances. And then the insulation in the cavity below ground is likely to be a more rigid foam of some kind rather than, for example, wood fibre insulation where it could be above ground. And again, the same detail for timber cladding. Very similar, so less to say on this. The insulation below ground is protected by what I've called a durable board or panel. Could be a cement board, for example. It could equally be bricks or blocks. And now I'm going to pass over to Beth for the next slide.
Hi everyone, hopefully you can still hear me. Just say if you can't, because I seem to be having some screen issues that I can't see myself. But yes, good. Right, so now we're going to look at just shout if this isn't coming through, and I'll wait for you to hear me. Now we're going to look at just a slightly different approach mainly to the foundations that might lead to some different details that are common on low energy projects, particularly passive house or AECB building standard projects. So here we've got a detail with an insulated raft foundation as opposed to a strip or trench foundation like Toby was showing. Good. So this might be useful because you can more easily do a low thermal bridge detail in this situation. So as you can see, the insulation from underneath the raft slab goes up the side of the raft slab and then is continuous with the insulation in the wall studs. So you don't have a thermal bridge around this junction. So some things to say here. I mean, sort of most of the detailing is similar to what Toby was saying. We've still got breather membranes on the outside. We've still got vapor control layers on the inside. What we've got here also on the inside of the wall studs is the air tightness layer, which connects directly to the raft foundation and with tapes. So what you've commonly got is an airtight OSB, which performs various different functions. So it's your vapor control layer, it's your air tightness layer, and it's also can be used as the racking layer for your wall panels. So it's OSB, or there's also another product which is essentially like a particle board, but they both do the same things. Then you've got your wall studs sat partially on the edge of the raft slab foundation. These that I've drawn here would typically be I-joist, engineered I-joist wall studs. So yeah, so you could do that. You could also do this detail with them, for example, a CLT panel on the edge of the raft, so something like that. How I design those wall studs is with all the load coming down the inner flange and then the outer flange being the cladding support. But there's ways to approach that design from different engineers. What you've got here also, the sole plate is worth mentioning here as well. I see a lot of details with an I-joist used as a sole plate, but going back to what Toby mentioned about use classes, you can't actually put I-joists in a use class 3 environment, and then also you don't have edge distances to be able to fix the I-joist down to the sole plate, just fixing through the side of a 38mm flange. So please don't use I-joists as sole plates. The way to do that would be to use either an LVL sole plate or a glue lam sole plate, something like that, or a softwood if you've got enough depth to do that. And yeah, so that's sort of the rest of the details on the outside are similar. You've got a sarking board there, which could be your breather membrane, could be an insulated sarking board. The one that's drawn is just a sort of MDF type of sarking board, but you can do insulated sarking boards. And then you've got the same cladding details as what Toby showed on the outside there for either a timber cladding or a render board type of cladding, or a brick slip type of on a board type of cladding system. And then moving on to the next detail, we're looking at here at an option for if you did need to do a masonry outer skin on this kind of system. You obviously, because your foundation is insulated and inside of your structure, you then obviously don't have any foundation on the outside to support that brick cladding on. So you're probably looking at a separate foundation. You can do concrete boots on the edge of raft slabs and that kind of thing, but they do tend to introduce thermal bridging. So if you can put the masonry cladding on a separate foundation, that's generally the best option for thermal bridging, although it does then introduce other questions around differential movement between the timber system and then the masonry cladding. So that needs to be taken into account in sort of around window details and wall ties and all of that kind of thing. But that's an option that you might use. Another thing which I forgot to mention on the previous details here is that we've set the raft slab at 150mm above ground level, so it's at damp-proof course level, so that then we can start our timber studs straight off. You can do things like do upstands on the edge of the raft slab if your floor level wants to be the same as external ground level, but generally sort of most straightforward thing would be to set your raft slab at damp-proof course level, and then you can go with your timber frame straight off that. And then I just wanted to mention quickly another detail that might be common in this. I hope you can still hear me because I'm getting no feedback. Yeah, here we go. Good. I just wanted to quickly mention another detail, and we're not going to get into enough time to talk about window details or lintels or any of that kind of thing in general. But I just wanted to sort of point out that with low thermal bridge details, particularly with larger glazed sliding doors, you come into sort of tricky situations of supporting those large heavy doors on the edge of a raft slab, where you're also wanting to put insulation beneath the doors to reduce the thermal bridging. So this is an option for how you might deal with supporting a door on the edge of a raft slab here with a little boot on the edge. There's other details like using steel or angles supported fixed onto the edge of the raft slab, but here's an option that might be applicable. You've got a block of structural insulation underneath your sliding door there that reduces the deflections at the sills of the sliding doors. So foam glass or compact foam would be something that would be appropriate there. And then you've got your concrete toe underneath the door there to support that. But yeah, I won't get into the rest of sort of window door detailing, thermal bridge detailing, because there's a lot to go into there as well, but that's enough for now. Oh, I forgot about this one. Yes, we've also got here a detail of how you might do a suspended timber floor, and then also just wanted to touch on how you might do piled foundations. These in this case that are drawn here are concrete piles, but you might do this kind of detail with a screw pile for a completely concrete free foundation and ground floor system. I won't get into that in too much detail because again there's a lot to go on here, but this has got sort of, you've got sort of suspended timber floor which has got its void beneath for the ground conditions, and then you've got some glulam ground beams in this case, spanning between little steel stub structures that then connect to the concrete piles, and again, like I say, you could do steel screw piles with this detail as well. This one, as you can see, and like Toby mentioned earlier, you start to get a very big differential between your ground level and your finished floor level, which you need to deal with in this building had a deck around it to bring the entrance level up to the finished floor level. So you've got quite a ramp to make up there. So that's where that detail gets a little bit tricky. But yeah, so that's me for now. Back to Toby.
Thanks, Beth. And so moving on up through the building, we're at first floor now. The detail we're showing here is, in timber frame parlance, what we call a platform frame, where you build the first story of walls and then place the first floor on top of the first story of walls, and then build the second story of walls off the first floor. Going back to our key themes of starting with moisture. The DPCs now will be around all the openings in the external wall. I'm not showing it here, but windows and doors will have DPCs on the jambs vertically and top and bottom horizontally. The cavity is maintained behind a brick cladding. Breather, membrane and vapor control air where they were previously on the cold and warm side respectively of the insulation. Fire, we've got one more thing to talk about here, which is as well as the fire linings to protect the timber from burning. There's we've got a cavity here, and smoke and fire traveling through cavities is a real risk. The rules for cavity barriers in small, so we have a cavity barrier in the cavity to prevent that happening, smoke and fire traveling through the cavities. The rules for cavity barriers vary between England and Wales and Scotland. They tend to be a bit stricter in Scotland, and I would suggest the Scottish practice is better practice, and that would require cavity barriers at each floor level and at returns on walls and around windows and doors. Now, in this case with brick cladding, there are a number of different cavity barriers you can get, from mineral wool to solid timber and others, and we're showing that cavity barrier just below the floor level in this detail. There's a very good reference document from the Structural Timber Association on cavity barriers, which covers all of this in detail. And we've also got one more thing to note here, which is about disproportionate collapse, so stability. Now, a single family dwelling, assuming it's of a modest size, is likely to be consequence class 1. I feel it never hurts to design some robustness into buildings, even if they're class 1, and you could be strained class 2A in smaller buildings. Again, luckily, there's some fairly standard guidance for how to connect the floor into the wall, i.e. what nailing to use to achieve Class 2A. We'll cover that on the next slide, but you'll see it does involve the floor deck going into the wall continuously rather than stopping at the face of the wall. One quick thing to mention here, if you're not used to timber frame, is that in concrete or steel buildings, you might find the brick cladding supported at each floor level on, say, a shelf angle, whereas in timber frame, pretty much regardless of the height of the building, the brick cladding will be supported off the foundations. So in a two-story building, you have 2 stories of brick cladding. This next slide quickly just references those nailing requirements. That's in PD 6693 for Class 2A disproportionate collapse, and also the guidance from the Structural Timber Association on cavity barriers. The next slide is again just swapping out the brick cladding for timber cladding. Very similar, except this time the horizontal cavity barrier we've got it has a difference, because we couldn't have a permanently closed barrier in this case because it would disrupt the ventilation behind our timber cladding unless we ventilated below the floor and above the floor. So often you'd use in this situation a intermittent cavity barrier for the horizontal ones, which would otherwise disrupt the ventilation behind the cladding, otherwise known as an open state cavity barrier, which only closes in the event of a fire. I'm about to hand over to Beth, but I'd also just mention in platform frame construction, a roof, a flat roof would look very much like this, but of course wouldn't have the extra story on top, but the roof would sit on top of the upper lift of walls in the same way this floor does. So Beth, back to you.
Thanks, Toby. So yes, Toby mentioned there that his details relate to platform frame construction, which is the most common type of timber construction in the UK. What I'm going to talk about here are how you might detail with balloon frame construction, which is more common in other parts of the world, but also more common in low energy buildings and passive house construction. So, and that's because you can then have a continuous air barrier on the inside face of your wall studs through your floor zone. So here we've got the typical detail of a floor connecting to the side of the wall studs via an LVL ledger beam. What you do to ensure airtightness behind this junction is to typically run a strip of airtightness membrane up behind your ledger beam before you install your ledger beam. And then when you come to install the OSB racking board later on, you then tape that membrane to the racking board. You can theoretically do airtight buildings using platform frame construction, but what you end up doing is lapping a membrane round your floor junction into the wall, outside, back into the wall, which is very convoluted, particularly around corners, and it leads to risks of damaging that barrier during construction. So it's much easier to achieve a much better airtightness result with an internal continuous a layer with a platform frames construction. That's a sort of a side note on that. But so basically structurally what we've got here is the floor.
Oh, you've gone quiet.
Oh gosh, this, can you hear me again?
You can, yeah. You went
better.
On
mute, gosh, yeah. I'm having issues. So yeah, so what you've got, the floor connected onto the side of the wall studs using mechanical screws and joist hangers. So that's all pretty standard construction type of stuff. There's probably not a lot more to say on that. I guess the only other thing to say about platform frame construction is that because we use a balloon frame construction, because we use platform frame construction pretty much predominantly for timber frame in the UK, all of the details like the disproportionate collapse details that Toby mentioned are designed for platform frame construction. So there aren't easy rules of thumb for detailing balloon frame construction for a situation where you need to do disproportionate collapse details. So there are ways around that, and you can prove that from first principles, but it gets a bit more tricky to detail larger structures using this type of method, although it's not impossible, just a bit more thought required into it. And then, yeah, the next detail here that we're going to talk about is what I call a sort of partial balloon frame, where we've got because the other tricky thing with balloon frame is that because you've got your full length of your wall studs going up in one go, your temporary works requirements in terms of scaffolding and stabilizing those wall studs during construction is more intense than would be for a platform frame construction. So we get builders asking if they can do something between the two, which was where this detail comes in, where we break the lifts of the floor of the wall studs just above each floor level. The reason for it being just above the floor level is so that then we can still maintain our continuous air tightness line above, and we've got a nice space to tape above the floor level to make a continuous air tightness line past the floor zone still. But we're bringing in the benefits of a platform frame construction where we're not having full sort of, I don't know, 5-7 meter high wall studs hanging around on site and needing to stabilize those during construction process. So we've got a sort of first lift of wall studs, then the floor joists come in, and then we go up with the same detail going further up the building. Yes, and I'm just going to touch on roof details here. We're not going to talk about these too much because, as Toby said, they are kind of similar to floor junction details. I'll just talk about this sort of rafter to wall junction here as in terms of engineered eye joists. The main thing to note with engineered eye joists is that you can't bird's mouth them or notch them over wall plates. So they need to sit fully onto the top of wall plates, and the inner flange of the rafters needs to have full bearing onto your wall plate at the top of the wall. So just generally leads to a little bit more sort of space being taken up with the rafter to wall junction there. And then the next detail might be if you didn't have space for a full lintel under your wall plate. If you just skip on Toby, although I might just not be seeing the thing moving on. There we go. Here's what you might do if your windows are pushed right up into the eaves junction here. So what we've done here is we cut off the rafters and put them on joist hangers, and then they're fixed to the side of an eaves beam, which is also forming the lintels over your windows at eaves level. So there's a couple of ways to approach those junctions depending on what situation you've got. And then I think finally we just got a little ridge detail here, which is again would be a passive house ridge detail where you've got your continuous rafters over the top of the ridge beam so that we don't have any thermal bridging. And then the only thing to note here is that you end up with some pretty hefty screws to screw from the outside of the eye joist all the way through into your ridge beam at the top there. And then I'll hand back to Toby.
Thank you. So I'm going to hammer home this moisture thing. It's really important to keep timber dry. So think about, again, don't just rely on the typical details, but do think about in your particular case where the sources of water and moisture could be from. And if something does go wrong, what will happen? Will there be any warning before the rot progresses too far? Will it dry out? This little image here shows two obvious sources of water, which is from the ground through your wall somehow, or from leaking pipes inside. You see here an internal wall, which was built directly off the slab, could be particularly vulnerable. And it may well be good practice in many cases to raise that above the slab too, so that should there be a leak or water pooling there, which you're not aware of for a long time, or the owner of the building is not aware of for a long time, it won't be on the timber. The other images here are of a timber post, which was in the ground, so it was fairly severe use class 4. Treated with a well-known preservative for use class 4, and in theory should have had a life of 15 years or more, but it failed within 5 years, as you can see pretty drastically, purely because the timber they used was quite hard to treat, and the preservative did not penetrate as much as it should have done. But it really goes to show, even where you don't rely on preservative treatment doing the job, the detailing is the first defense to moisture. And then once you've detailed it to prevent moisture affecting your timber, then you're relying on preservatives to help with the rest of the equation. And quickly one from Beth here too.
Yeah, this is just a detail from, this is a raft slab, which is 150 mil above ground level, so it is at DPC level. But this, during construction, obviously your raft slab sat there flat with moisture potentially sitting on it. And in this instance, we'd used a plywood sole plate instead of an LVL or a glulam sole plate. Just partly that was early on in our progression with these details. So not something I would do again for this reason. So obviously the plywood is sat there then in the damp, because it's sat on a flat raft slab for a while until they get the roof up and the building weather tight. And we just found that the plywood, it did depend on what type of plywood it was and the manufacturer, but it was delaminating, so they needed a good chunk of this sole plate replacing during construction process in order to just because it hadn't lasted even the construction process. I've also seen a similar thing happen with LVL that was kept outside before it came to site, so it had been stored at the yard outside for a good 6 months, and then when it came to site to be used as a sole plate, it was then already delaminating. So yeah, something to just keep in mind, even when you have got your timber 150 mil above ground level, that it can still, the construction process matters, and keeping it dry during construction matters.
Yeah, and so on that point, during construction, it's not just about end use, and the contractor should take active measures to protect timber during construction. Ask about their moisture control protocols. It's okay if timber gets wet. Structurally, it's okay if timber gets wet if it's allowed to dry out soon after, regardless of any preserved treatments and use classes and so forth. But prolonged exposure can be an issue. And it can also, even brief exposure can cause staining. So if you've got exposed timber, difficult then to remove. So here we see a number of examples of how not to do it, and one example of how it can be done very well. And there could be happy mediums on your projects, but it's something that the contractor should be thinking about and telling you about, so that you know what they're meant to be doing to prevent moisture issues during construction. One other thing that comes up in timber buildings quite a lot, more so in multi-dwelling buildings, i.e. flats, where you've got party walls and party floors, is the acoustic separation. A concrete slab provides the acoustic separation quite easily, timber floor less so. Luckily, there are things called robust details which are published. You can look them up, and they'll tell you if you follow the robust details exactly, you can avoid a pre-completion acoustic test potentially. If you follow them exactly, you'll probably exceed the acoustic requirements quite considerably, which is no bad thing, because there is some leeway in there. But very important to consider at an early stage. It can affect your build-ups and by which I mean your floor thicknesses and wall thicknesses. The sketches there just showing the kind of sources of noises that we're trying to deal with, which are effectively airborne noise and structural-borne noise. There's also some trial guidance on this, acoustic performance of residential timber frames and so forth, which you can look up. But really, reach for the robust details if you are doing separating walls. They can get quite complicated. So the next slide is just going to show the kind of level of detail you might end up having on drawings where you've got separating walls and floors. These are the depths of the floors here are sized to suit the robust details. So then it's also fortuitous if you can use that side to also be the right size for the span you're trying to, structurally for the span you're trying to cross. There's a number of, lots of details tied up in here. I'm not going to go through any detail. It's really just show the level of detail you might need to consider, from robustness in terms of structural sense to robust detailing in terms of acoustic sense. And the two things in acoustics resilience you're looking for is mass. And so you'll see here the layers of kind of heavy things like plasterboard and plasterboard plank added, and isolation. So the ceiling is on resilient hangers and the floor is on resilient foam battens to stop the impact noise going through. That, I think, to the minute, wraps us up for our 40 minutes of talk, hopefully leaving lots of time for an active Q&A.
Thanks, Beth and Toby. We have had lots and lots and lots of questions in. I'm trying to cluster of them so they make sense. Are you happy that I just dig in and ask them?
Well, if you ask easier ones first, that'd be nice.
Okay, well, you'll start with Beth. From Luca. So obviously there's been a lot of thank yous already, but Beth, could you expand on the benefits of EPS underneath the raft slab, and are there any other options?
Yeah. Do you want to skip back to that slide, Toby, just so we can talk about it whilst we can see it as well? Yeah. So where do we start? It's possibly worth talking about this in combination with Toby's details as well. So there's a few benefits to doing an insulated raft slab. So like I said, you've got your insulation continuing around the side of the slab and up the side of the slab. You've actually got a positive thermal bridge there in terms of you've got extra insulation around the edge of the raft slab compared to the rest of the flat bit of the raft slab. There's a sort of side note on that. If Toby, do you mind just skipping to your detail, actually, one of these ones? So you can see in either of these ones, we've got a section. So we've got insulation in the floor zone, which is one thickness. Then we swap to some sort of insulation down the cavity there, which is a different thickness. But if it's a bit difficult to explain without sort of therm bars, but you've got a junction around the base of the masonry there, where the masonry that is attached to the ventilated cavity. There's also a sort of a pathway for moisture for heat to transfer around the side of the wall plate there, sort of round into that junction there that Toby's just sort of pointing out, into the cavity, into the ventilated void beneath the floor. So you could add extra insulation on the inside face of your below ground masonry there to reduce that thermal bridge, and then there are ways that you could do that. So that you've got quite a nice continuity of insulation between your below DPC insulation up into your timber wall, so that's quite a good junction. But you've got more tricky details there around that floor to wall junction, mainly because you've got lots of different materials going on there. So it gets a bit tricky to completely remove all of those thermal bridges, and it's not that that isn't a way that you could achieve for example, a passive house building. There are passive house buildings that have that kind of detail. You just end up with a lot more layers of insulation, a lot more tricky details around air tightness. So the benefits, going back to this detail, thanks Toby, is that then you've got your continuity of insulation right from your raft slab right up into your wall studs there. You've also got continuity of air tightness direct from your internal OSB there, direct. You would tape that to the top of the raft slab there, and that would be a fully airtight junction. It's just in terms of simplicity of detailing, rather than, it's not necessarily that you can't do other ways of detailing it. It just makes it the thermal and the air tightness junctions a lot simpler. And then from a structural perspective, I like being able to connect, if I do need holding down straps, I like being able to connect them directly to the raft slab foundation there, rather than having to go through layers of below ground masonry, or for people to fix their holding down straps to the below ground masonry, which is not suitable, or to try and fix their holding down straps to the floor slab, which again is not suitable because there isn't enough mass in either of those things to do any kind of holding down capacity. So I like the fact that there's less to go wrong in terms of fixing holding down straps directly to your foundation there. And they're not a thermal bridge, because that's another thing about holding down straps, as they become a thermal bridge. Hopefully that gives you some ideas of things to go on. There's lots to say there.
There's a huge amount to say, and actually we'll be coming back to some of those. So this is from Ashley and for Ewan. Read the first two insulated raft slab details. The overhang of the sole plate looks rather large. Is it partially bearing on the EPS foam, or are there other brackets needed to bring the load back to the reinforced concrete slab?
So yes, it does look quite large in that. I tend to keep it now to around about a third of the depth of the wall studs, but there's no guidance on how to design that kind of detail structurally, although you could work it back from first principles. But so I tend to keep it to about a third of the depth of the overhang to a third of the depth of the eye joists. Now that's slightly different in that detail, but there we go. And also, so no, I don't design the EPS as having any bearing underneath the sole plate, mainly because it would be a different capacity to the to the raft slab, so you would always get some differential settlement anyway in that junction. And I design all of the load coming down the inside face of the I-joist, so that then the rest of it is cladding, or would be sort of similar to, as architects love to call it, a Larsen truss idea, where the external face of that is just supporting the cladding and containing the insulation. So the structural work is being done, and if I've got any posts or anything like that going on, they always come only down the inside face of the I-joist. So that's how I reconcile it in my head. It would be great for there to be some more research onto this and some modelling done as to how these walls perform, particularly from a racking perspective, from the manufacturers, but there isn't at the moment. So there we go.
No, thank you, Beth. This also leads back to that. I don't know if it's for you or Toby. So this is from Alex. How is the load transferred to the foundations or the raft slabs when you're looking at the I-joists? How do you actually transfer the load?
From transferred from the I-joists.
Yeah.
I mean, your I-joists there, I mean, it may not be super clear, but they're effectively just at the full width of that wall stud. So the sort of the thinner sections either side of that detail are the flanges of the I-joist. So we've got all of the load coming down, thanks Toby, down that inside flange there directly onto your raft slab. So I feel like there was probably more to that question, but I didn't fully understand it.
Yeah, there was no more in there, but I mean, I suppose, how do you actually attach it? So you're screwing down into the raft?
Yeah. Oh yeah, that's good. That's a good point. Yeah, so you're screwing down from your sole plate. It gets screwed horizontally down into the raft, and then you've got holding down straps if you need them as well. And then your wall studs you've obviously got your racking board containing all of that on from sole plate into wall studs as well. But yeah, your wall studs get screwed down into your sole plate as well.
Thanks, Beth. And so Lucy and Ashley, so again, probably two similar questions. In the first slide of the typical details first floor, the section is for joists perpendicular to the wall. How is the detail different when the joists are parallel to the wall? Do you essentially have two rim beams?
Yeah, 1 second. I'll just bring it up. Here we are. It would look very similar, except exactly you'd have two, where we've got the header joist mark there, you'd actually have two of those, and then the joist immediately adjacent to the wall would be in this area here.
You actually had it on your section from the PD document that showed one with the joist parallel.
Here we are.
Yeah.
Yeah, it's slightly different because they're using things, but here effectively this is the first joist, and that would be the header rail. I've got a slight separation in my one, but it's the same principle.
Oh, brilliant. And this is probably which you're just showing in those, and maybe in the robust detail as well. How do you tie vertically between the stories if net uplift or overturning is critical on upper levels?
Right, let's see, first floor. So yeah, I've got an orchard here, possible uplift at first floor. I mean, you'd be unlucky to get uplift at first floor, but it can happen. And you can, well, there's several ways to do it. Two obvious ways. One, you screw it down well, or you add some straps. Obviously, you'll have quite a bit less uplift at first floor than you would at ground floor in a two-story building, and a little bit less load to hold it down with.
Thanks, Toby. And I don't know if this is a statement or a question. Cavity trays are required over horizontal cavity barriers?
Yeah, so you can see I've suggested a cavity tray in the detail here. I haven't specified exactly where they all go, but yes, and that will also apply over windows and things and doorways as well.
Brilliant. Question from David. About support masonry cladding to timber frame. It's David's understanding that the purpose of the support angles at typically 9-meter vertical centers was to address thermal movement in the masonry. Surely that problem still exists with a timber frame building once it exceeds 9 meters in vertical height.
Yeah, so the reason that brick cladding in timber frame buildings sits on a foundation is because there's not much practical choice. But it is very true to say it's not just thermal movement, but differential movement, vertical movement full stop is the issue to think about in brick cladding on timber frames. And the higher, more storage you're building, the more significant it will be. But there are examples of 6-story timber frame buildings with brick cladding off a foundation. In that situation, you'll be thinking very carefully about the differential vertical movement between the timber frame and the brick cladding. And there are a number of effects which deal with that, not least the squashing of the timber across the grain at sole plates, where it's least stiff, taking up slack in those areas, vertical loading, elastic shortening, and thermal movements. And again, there's quite good guidance on this from the other lot, the STA, about how to deal with that and research on it. So we're covering low-rise buildings here, where over 2 stories, it's worth thinking about the differential movement, but is unlikely to be a serious problem. But for higher, taller buildings, you should definitely be thinking carefully about the differential movement between brick cladding and the timber frame.
Oh, so thanks, Toby. And yeah, echo your points on the Structural Timber Association and their detailing. And yeah, they should be able for you to access. If they're not, just give us a shout at TDUK. We have an MOU with the STA. We just all want timber buildings to be designed and built well. Disproportional collapse from Luca. Regarding disproportional collapse and referring back to first principles, I think you were speaking about this, Toby. Did you mean over design of elements and fasteners to address it?
I think this might have been when Beth mentioned about balloon frames not having the easily available details.
It probably was me.
Mm.
Yeah. Yes. Yeah. A way that you can detail timber buildings is to use a ring beam method and then deal with sort of, I forget what the terminology is, but where you lose a panel within the set and you checking the impact of that on the structure. The good thing about that method is that you do already sort of have a ring beam around it with your floor ledger beam, so you can design that as your ring beam. That's one way to do it. Yeah, the reason for the details that they do in that PD document is because getting the forces that you have to design for other materials around a timber structure is very difficult. So they've sort of lessened the criteria with those junctions for platform frame construction. What you don't really get is the lessening in for a balloon frame structure. But yeah, there are ways to do it, and you obviously do have a lot of redundancy in the structure in terms of a lot of wall studs, and so there are ways to go around that. But yeah, probably the most straightforward one is to design that ledger beam there as a ring beam, and then you can deal with it that way.
That's a key element method I think you're referring to.
What's this?
The key element method, I think.
Okay, there you go.
Yeah.
I don't do a lot of those, sorry. Sorry, everyone.
Thank you. And staying on the balloon frame, from Alex, do you infill the webs at joist locations? And I don't know if it's talking about actually structurally infilling them or insulation infilling them.
So structurally, you do infill them in certain locations, mainly around the roof junctions, where mainly where you wanted to do web blocking from a structural perspective is if you're cutting the I-joist not square. So I sort of showed those a little bit on my roof junction details, and you can find all of that information about. I didn't sort of share them on that. Sorry about that. But you can find all of that information about where you need to do web blocking from a structural perspective in the I-joist manufacturers' typical details. So they've got loads of information on that, all of the different manufacturers that you can get. And then from an insulation perspective, yes, they are filled, but the little boxes that you create between each stud are filled with insulation. Yeah.
Thanks, Beth. And Aaron is asking more about balloon frame details. Is the LVL ledger just screwed into every I-stud? Considering that the I-stud flanges can be narrow and the OSB webs interfere with the screws, this seems like a difficult detail to support larger floor spans. Possibly harder to justify the ledger fixings.
I mean, yes, they are fixed into every wall stud. Generally, the web doesn't get in the way of the fixing capacities of the timber. Particularly Styco have done a lot of research on that, and the web the web blocking doesn't typically get in the way of the detailing. So yeah, you can fix into, you've generally got a minimum of 45 width of the flanges of the wall studs to fix into, but if you did need more capacity, you could do wider fixings. I'm using just structural timber screws, so sort of 6-ish millimeter wide on those kind of fixings. What I don't tend to use are I see a lot of people still specifying coach screws, which are just like massive, so sort of 10 mil diameter up, and yeah, you're not going to get any coach screws to work on a I-joist timber frame, but yeah, it's sort of standard structural wood screws, which have got a really decent capacity anyway, and you can design all of those fixings to the Eurocodes. They're pretty straightforward. Yeah, so that's what I'm doing.
Thanks, Beth. Ashley, more about, again, keeping things dry. Is there any formal guidance on how long OSB or plywood can be exposed to the elements on site during construction phase? Example, wall sheathing or sarking?
Well, it depends on the grade of the OSB and the plywood. So sheathing would typically for OSB be specified as OSB 3, which has some kind of resistance to moisture. And certainly for the typical exposure times would be okay. The important thing being that it doesn't go away, closed up while still wet without a chance to dry out. There won't be guidance that will tell you how many months or weeks something can be wet for. But typically on a construction site, things shouldn't be staying wet for long term because it'll be rain, which should dry when it stops raining.
I was just going to add to that you can sometimes find information on that in the manufacturer's guidance. I'm thinking particularly in terms of things like insulated sarking boards. They will generally tell you how many weeks or months they can be left exposed without cladding being or another membrane being put on top of them on a construction site. And then the other caveat is around just the quality of the OSB or ply manufacturers, particularly at the moment. There was a moment sort of around lockdown time where a lot of the glues were getting very watered down and the quality of the products was pretty poor. So that's something to just keep in mind, that not all OSB or plywoods are created equal, despite the fact that we just specify OSB 3 or whatever from a structural perspective. Yeah, they are not all the same. So having a look at the manufacturer's information is useful, although it may not always tell you how many weeks or months it can be left exposed.
And then summer or winter or autumn or spring, it's also different.
And then whereabouts in the UK it is, which varies wildly. So yeah.
Seaside and stainless steel fixings as opposed to coated or plated. Well, a huge thank you to you both. I know we haven't quite got to all the questions. I think we've hit the most relevant ones. Yeah, a huge thank you to Beth and Toby. You can find them both on LinkedIn or Twitter or other forms of social media. I think they're always ready to reach out to them, follow them. Timber Development UK, we host lots and lots of resources. Some of them we put into the chat, but just go on the website, check them out, just reach out to me. You can find me also on LinkedIn and we will hopefully point you in the right direction. Next slide, Toby. We run a student challenge, so any of you who are lecturers or students who want to come and join us, we will be talking about affordable timber framed sustainable homes. So obviously some of the detailing you've just seen would be really applicable. Next slide. And next week is our final webinar, which will be about building with timber on the 17th of October. You can catch up on all the webinars on our YouTube channel, which we'll put a link to in the chat. And final slide, please, Toby.
That's it.
The one is missing with who we're going to have next week.
Oh,
and that's what I'm sure you cut it off. But so we will be joined by Oscar Emmanuel from Xylotech and Eleanor Headley from Field and Fowles. So we have a project manager and an architect to wind up our series on engineering with timber.